My service at NASA and NACA began in 1942 and ran through 1980. Major research areas included subsonic, supersonic, and hypersonic aerodynamics, propulsion, and reentry. The interviewers today are Scotty Springston, Don Byers, and Kerry Wren, and on the camera and sound are Elizabeth Gibson, Dieter Ivey.
Thanks, Ken. You had a very interesting early background that got you interested in aviation, and I wonder if you could talk a little bit about the environment that got you started.
Well, I was born in the air capital of the world in those days. More than 20 aircraft factories were located in Wichita, Kansas, where I was born. And at a very young age, 6 years of age to be exact, I found myself in Dayton, Ohio, on my way to my grandfather's funeral with my dad, stopping over in the Dayton Hotel. And that night there was an extra on the street, "The Lone Eagle has landed in Paris." And that was the beginning, you might say. And that Christmas, my dad gave me a copy of the book We that Lindbergh had written. So that's kind of where I got started. And that moves on, though, to because my next door neighbor was the chief test pilot for Walter Beach in the Travel Air Days about 1929. And Walter had designed a very secret ship called the Mystery Ship, which Earl Hutton, his chief test pilot, flew. And I observed that first flight out at the old Travel Air Place just a couple of miles from where I lived. And he and his wife didn't have any children, and they kind of adopted me, and I got a chance to meet all the aviation notables in those years of 1930s and all. I guess my real first, you might say, concern for NACA developed in high school when the son of our principal came back from the Bureau of Standards to talk about his experiences, and then told about the Langley Memorial Aeronautical Laboratory of NACA down there at Langley Field. And it was at that point in time that I decided I wanted to work there someday, and I set my sights on that goal from that time. I went to school at the Wichita University in those days, now Wichita State, graduated from the University of Michigan in 1942, and I was able to do experiments in their wind tunnel there under Dr. Stalker on boundary layer control. And as a result of that, that kind of shaped some of my early days. And I also formulated the first experimental course in aerodynamics and taught it the first year it was taught there. And Jack Reeder, who was formerly test pilot, a chief test pilot for NASA, was one of my first students, I might say. So I had a lot of fun doing that. He preceded me coming down here by about 6 months. And when I arrived here in June of 1942 and was interviewed by Elton W. Miller, the head mechanical engineer, he said Abe Silverstein had been kind of forewarned by Jack Reeder and wanted me down there at the full-scale tunnel. That's how I got started, 1942 in June.
What was one of your first projects at NACA?
Well, one of my first projects was to be assigned to work for Charles Donlin, who was then designing the new 7 by 10 foot high-speed tunnel. And I had to calculate all the boundary layer growth from the big restrictions at the entrance section all the way up to the test section. And that was done with comptometers and all kinds of simple mechanical and useful graphical techniques. We didn't have modern technology of computers in those days.
And then you told me something about nacelle design for the B-24s. That was right.
Oh, in 1943, they had sent a bunch of the B-24s down to the Libyan desert, to Tunisia down in there. And the first of those, when they sent them out on missions, arrived back either not sufficient power to make it back home and augured in, or they came back on less than 4 engines. And we got a real hurry-up call from headquarters and from Pratt & Whitney to find out what was wrong. A small team of 3 of us were assigned on a Friday morning by the H.J.E. Reed, who was the head of our facility in those days. Engineer in charge was his title, and Abe Silverstein was my section head, and 3 of us were assigned to get that thing ready as quickly as possible. I had to get all of the cowlings and all of the nacelle metals built for a test stand that had to be still built, and we installed the engine on Tuesday morning. By Wednesday afternoon, we had sufficient data. We knew what the problem was. It was a double-row engine. The rear cylinders were overheating, burning the valves up, and we actually built and installed baffles to obtain the cooling that was needed. And they were shipping those over by air on Saturday. That's how quick that one was solved. A very fascinating little project, but very critical to the success of the use of those airplanes.
And I presume they were, that was standard from that point on.
Oh my, yes. Lots of airplanes came through our place. One of the first things we did was to use old-fashioned modeling clay, which we called mud, and lots of tape, and we covered up every opening, every crevice, every step, anything on the airplane that was a drag producer, and then we'd get a clean airplane drag measurement in the full-scale wind tunnel, and then we'd begin to open those things up and find out which contributed what, and then we could make recommendations to the manufacturers. Many changes were made in the field on those. And one of the big ones happened on the old Douglas Dauntless airplane. They were done out in off of Honolulu, and actually they cut the stuff out there and made the parts, and they added about 30 miles an hour to that airplane, which was sufficient when the Battle of Midway came along, that when the Japs came down after them, after they had dropped their torpedoes and got rid of their bombs, that the airplane had enough on-the-deck speed that when the Japs came down on them, most of them augered in because they couldn't pull out fast enough because they were only 10 feet over the waves. And so that was one of the big things. But we added lots of speed to many of those World War II airplanes, just doing that sort of thing.
What was your next major project after that? Anything else during the war?
Oh, yes. I was involved with boundary layer control, getting some basics research done there, and then getting into air inlet technology, which we'd done a lot of work on nose air inlets and cowlings, which was very adequate, but we had very little information on side inlets, air scoops, and that type of device, which with jet engines were beginning to make a very important place in the world. And so I pioneered the work on side inlet studies at low speeds, then moved over to the 8-foot high-speed tunnel where I carried that on to transonic speeds, using new technology in building models even, because we had very sophisticated models for the first time built of fiberglass. And by the way, Ed Kilgore, and whose wife was the mayor of Hampton for a good many years, was my engineer in designing all that fiberglass stuff, and our shop head got a certificate of merit out of that, because that was all new technology. After that, nearly all models for the wind tunnels were built of fiberglass. That was kind of a fun. I had a lot of fun in my career, I might add.
It looks like you did. Then in the 1950s era, you were working on some of the advanced aircraft of the Air Force aircraft and Navy too. What were some of those aircraft and what kind of work were you doing?
Well, first of all, let me say that Dick Whitcomb was starting to do drag studies and wondering about transonic speeds. We'd gotten our first slotted wind tunnel in 1950 when the 8-foot tunnel was modified with slots so that we could go continuously through transonic speeds. Authorization to build an 8-foot transonic pressure tunnel also was authorized by Congress, which was completed in 51 or 52 or thereabouts. And so we did work on all of the airplanes of the day, and the F-102 was the first major breakthrough because the 102 was supposed to be transonic but wouldn't fly past about Mach 8. And with the shaping, the Coke bottle shape as it got to be known by everybody of Dick Whitcomb's work. But I had the privilege of working on a lot of those early studies and assisting him with that. And out of that, I actually did work on the F-11, which was the first airplane that was designed to fly through the transonic speed from scratch. And that was fun. And then the F-8U-3, which was the first Navy airplane designed that way from scratch. Unfortunately, it never saw very much service because the McDonnell airplane with twin engines came along. And I was involved with that one because they messed up on the scoops on that one. So they used my old data that had been generated at in the earlier period of the early 50s on air inlets at transonic speeds. They used that to fix that airplane up.
And what was that, McDonnell aircraft?
That was a McDonnell aircraft, yeah. That was the Phantom F4.
Okay.
And then I worked on the swing wing TFX also, and some of the drag rise studies associated with that. Those were fun jobs too.
Let me back up. You mentioned the slotted tunnel. What was that for?
That was to obtain smooth flow through transonic speeds, because as you approach transonic speeds, shock waves develop, and those shock waves would extend completely across the wind tunnel and block the flow, so you could not go any faster. What we did was, in the early days, we would go up to about 0.85 Mach number with our tests of a model, and then we had a plaster liner in the throat that we would shift the model to the new plaster liner area, and we could actually operate the tunnel at 1.2 Mach number then. But we couldn't get any data in between. And so the slots relieved the constriction caused by the shock waves and allowed us to move smoothly through the transonic speed range.
Well, in that period, you were getting into looking ahead to space, I think, and you got involved in some research on in that particular field, didn't you?
Well, actually, my propulsion background that had come along got me involved in a number of different things. I was involved in the Bumblebee project under what turned out later to be ARPA at JPL with Bill Avery up there. Dr. Bill Avery, a very fine researcher up there. And that was on scramjets and ramjets and all kinds of those newer, higher speed devices. Tony Ferry flew some models at scramjet speeds, by the way, and tried to fire supersonic scramjets under an Air Force contract, and I was involved with that as well. And that got me involved also then finally with Bernie Schriever out in California, who had just formed the new Missile and Space Division, and I was the NASA representative, representing aerodynamics primarily, to a rather interesting conference in which the subject of space retrieval and repair in space was the primary subject. That was in around 1957, 8, somewhere along in there. I've forgotten the exact year. But that was but that kind of got me started in the space activities, and I got involved in some of the very early dinosaur work, the X-15 work. In fact, we did the transonic test data for the separation of the tanks on the X-15. That was a totally successful program. And we did that aerodynamic work in the 8-foot tunnel. And then we moved on into recoverable boosters, as we called them then, horizontal takeoff, vertical takeoff, all kinds of configurations, parallel series arranged vehicles, and we got lots of aerodynamic data. And as a result of having a lot of that data, I worked with the Marshall Space Flight Center under von Braun and his Future Project Office on many, many study contracts. I represented NASA and the aerodynamic side of the house for all of their studies over a period of some years in the 60s.
In connection with this, the re-entry, you were studying probably in the tunnel some of the heating and aerodynamic effects?
We were not studying any heating. That was all done in our structures group. They had facilities that were designed for heating. Ours was primarily aerodynamic, looking at aerodynamic stability, control, drag at transonic, subsonic, and even up through hypersonic speeds. And we did a lot of things of that nature in that day and time, looking at some of the lifting body shapes even in those early days. Dinosaur was one of the first ones. HL-10 came along, which is kind of the precursor ultimately to shuttle a little later. There was an X-24 Air Force program in which they flew 4 vehicles that were models of the X-24, and they were called the prime vehicle. That was precision maneuvering, including maneuvering reentry. I'll get it all straight in a minute. But 2 of those vehicles, built by Martin, by the way, were successfully flown, and they set the stage for later shuttle capabilities because they flew cross-range 1,200 and 1,500 miles respectively on a reentry program as a lifting body. And later on, I got a hold of one of those vehicles. Nobody knew where they were. I found them, and I got a hold of one of them, brought it to NASA, and we actually put that model in the 16-foot, well, we call it transonic dynamics tunnel in those days, and measured the aerodynamic characteristics of a reentry vehicle with ablative surfaces. And that was the first.
What kind of surface? With
ablative surfaces. That's that burned cork stuff that was on the leading edge and the lower body. And we brought that vehicle into the shop area out of a crate. No human hands had ever touched that surface. Gloves had been on everybody's hands as they recovered it, washed it off and crated it and carefully packaged it in plastic. And when we got it and uncrated it and had a nice rope around it, who walks in, unbeknownst to anybody, but the director for aeronautics, Larry Lofton, and I was walking into the room just as he got underneath the rope and was about to put his hands on it. He said, "Oh, I want to feel what that feels like." I yelled at him. I said, "Get your hands off of that," which he promptly did. but one of those interesting little episodes that happened. But we got interesting information on that with the ablative surface, and then also we had a model that had the plane surfaces on it, so we could get a reference point. So that was a fun project too.
Let's move on to, you said X-15 tank separation studies?
Yes, well, the early X-15 did not use external tanks, but when they wanted to boost it up to higher altitudes and speeds, they needed additional fuel. And so they added a tank to the X-15 on the underbelly. But the question was, what would be the aerodynamics of an empty tank as they tried to eject it from the airplane, and how would they do it? And I worked with the North American people on that. We modeled that in the 8-foot transonic pressure tunnel and got detailed pressure distribution data on the tank and on the vehicle. We were able to predict the tank separation characteristics under certain conditions, and that was actually the way it was separated when it did it. And I got a phone call the day of that flight that said, "Hey, Ken, we separated and it was great." And you know, that's the frosting on the cake.
Did you actually in the model and tests in the tunnel, did you actually separate tanks from the models?
We did not do it in free fall, no. We had them attached on their own force mounting stings, so that they were first of all in contact and then gradually separated to various angles, so that we knew what we were doing.
In 1967, you had done some interesting research in plume, the effect of rocket plumes, and I wonder if you could tell us a little bit about that.
Oh, that was an interesting one. In connection with the 8-foot tunnel, we had lots of capabilities because we had a fairly decent pressure vessel at about 4 atmospheres. We had a couple of large 100,000 cubic foot per minute compressors with lots of volume to them. So we built a little supersonic wind tunnel, hypersonic wind tunnel up on the 3rd floor in one of the shop areas. We called it a pilot tunnel, but we did lots of fun things in that. In terms of research, it was very practical, doing work with pitot probes and things like that. And then I decided that I wanted to try to do some simulation of the exhaust plume from a rocket engine. I was involved with some of these configurations that would require the separation, and we, my gracious, we had the Saturn program underway and other programs that were going to require separation still within the atmosphere. And the question was, what was the aerodynamic effect of the exhaust plume of the second stage engine when you light it off, just after you move it away from the primary vehicle? And so we simulated that, and it turned out that in that particular situation, we could simulate the approximate separation altitude of the Saturn V system as the second stage lit off. And we simulated the rocket engine pressure ratios in there using pressurized nitrogen for that. Schlieren photography to give us visual capability, which allows you to see the shock waves, flow separation. And one day, one of my engineers came into my office and showed me some brand new Schlerens on that. And I was very excited when I saw them. And I said, "Can you reproduce this stuff? And if so, I need it as soon as you can get it to me." We were using Polaroid cameras so we could get instant recovery of our data on a preliminary basis, and then we'd put it on large film cameras for permanent record. And a couple of hours later, he came up with a whole bunch more pictures of a lot of different test conditions. At that point in time, I called Huntsville. I said, "We got a problem." We were within 3 days of, I think it was what was called the A or the B launch of the Saturn V system. Now, there were about 5 unmanned launches of that vehicle. And I don't know whether it was A or B, but this was one of the systems launch, and the second stage was to light off. That much I do know. We were within only 3 or 4 days. They had predicted an LOS, that's loss of signal, of the radio system of about 3 to 5 seconds. Based upon the data that I had taken from that little model wind tunnel, I was predicting something like 8 to 10 seconds loss of signal. If that had occurred on that flight, they would have gone out into automatic abort mode. We would have lost all the second stage, and we would have learned very little. As a net result, after a frantic meeting the next morning, I might add, all the guys in the program department got busy on their program, modified the launch schedule, and we had a very successful launch. And the actual loss of signal was within about 1 second of the predictions.
So you had to increase the separation between the first and second stages before it lit off?
No, we increased the time of allowing the vehicle to continue on its path with a lost signal before abort would happen. That was the whole point. We didn't want to lose the mission.
But did you ever have a chance to talk to Dr. von Braun?
Oh, many times. I had lots of the work with the Future Projects Office and the contracts on various types of reusable launch vehicles over a period of 6 or 8 years with a fellow by the name of Dr. Hermann Kerle, a very fine German scientist under von Braun. I got very much acquainted with von Braun. In fact, I couldn't go down there and sign in without reporting to his office that I was on tap because he always wanted to contact me. Von Braun was a fascinating man. He knew everybody by their first name. You met him one time, and he called you by your first name the next time you saw him, anywhere you were, and it didn't make any difference. Fantastic memory. And also a very wonderful guy to be in a conference where there was highly technical material presented. He was a tremendous technical man, as well as administrator. But I have seen him in a conference with very deep technical material being presented, and when the conference would get over with, or when the contractors would finish their presentation, he would home in on the one most critical problem area and ask a critical question that often couldn't be answered right away. That's the kind of a man von Braun was. And you just couldn't help but like somebody like that.
What's the next big step you took? In the 1970s, you talked about some airfoil research.
Well, my work in the recoverable or reusable launch vehicles was beginning to wind down because Space Shuttle was beginning to come along and other people were picking that up. And so I had done a lot of the spade work, and that was very useful to them. But I had, wanted to move on to something else, so I was called by the division office one day and said, we've got an old wind tunnel that really we'd like to use if you think it's possible to use it. And it was the low turbulence pressure tunnel, which had been used for airfoil research many years before under Eastman and Jacobs and von Doenoff and those early birds, you might say, that did so much fine work. And the challenge that was placed before me was, hey, we've got a whole new airfoil technology coming along as a result of Whitcomb's work at transonic speeds. Those flat-top wind airfoils that he had designed for transonic use, could they be extended in some of that technology work at low speeds? So my job was to recertify that wind tunnel, which was another interesting job because it was a pressure vessel and required all kinds of upgrading to make it useful as a research tool. I even found some money and brought pipes down from the 8-foot tunnel from those big 100,000-foot compressors about 4 blocks down the road to bring that air supply down there so we could pressurize it more quickly. We put isolation doors in the test chamber so that we could bring the test chamber back up to atmospheric and do the work without depressurizing the whole tunnel because we didn't want to work under pressure like they used to have to work. And then we designed it to be able to test airfoils in 2 dimensions. And a whole new program called the Airfoil Research Program was born down there in that facility, and all the low speed work was done. There were a lot of contracts that were out in universities and grants and contracts. And that all culminated after several years in an international conference that I was privileged to plan and hold in 1978, where we had over 50 papers given by international authorities, and we had over 200 attendees from all over the world. That was a tremendous conference. In fact, I brought a copy of the conference paper with me just to make the point. But that was a fascinating thing. And as soon as I had completed that, I got the call from the division office again and says, we need you over here in the division office to be the chief engineer and to be responsible for the upgrading and recertification of all of the facilities. Oh, there was an interesting little thing happened back when I was recertifying the pressure tunnel. One day, Larry Lofton, who was our director for aeronautics at the time, walked into my office, plumped himself down in the chair, and looked at me and he said, you know, you're just a little over a block from Tactical Headquarters Command building right over there. He said, if this facility ever blew, what would it do? I said, it would wipe out that facility over there. I said, we've got enough volume energy here to wipe out the whole block right here. He said, well, I'm going to tell you something. He said, as long as you sit here in this office right next to it, he said, everything's okay. But he said, if I ever find out you moving somewhere else, I'm going to shut this facility down stat. I stayed, we ran the facility, and it ran for a number of years and still is operational.
What was the reason you were pressurizing the tunnel?
That was to get high Reynolds number, which is needed for flight simulation.
Okay, and what is the Reynolds number?
The Reynolds number is a property of the viscosity of the air, and at the highest Reynolds number of flight speeds, if you do not simulate it, then the boundary layer growth is not proper. Boundary layer separation characteristics don't behave properly, and so you get into all kinds of aerodynamic problems if you don't simulate that.
And that's related to the fact you're using models in the tunnel.
That is correct.
Compared with a full-size aircraft.
That's correct.
Okay.
With models that were roughly 2 feet in chord in that test section, we could simulate test Reynolds numbers of full-flight transport aircraft.
What did you do as chief engineer? And anything as interesting as previous work?
Well, that was work. We were preparing for the National Transonic Facility at that time. Actually, I had the responsibility of upgrading the full-scale tunnel, the 7 by 10 foot high-speed tunnel, recertifying those and other similar things. We had lots of procedures that we had to work out because in addition to wearing that particular part of the hat, I was also the safety engineer for the division. That meant lots of other fun things to be accounted for. The National Transonic Facility, which used nitrogen, cold nitrogen, to get the high Reynolds number at pressures, was a whole new technology. We had a model tunnel that had been operating for several years, with which I had also been associated in a kind of a peripheral fashion to that facility. And my situation that developed was construction of the new National Transonic Facility was moving at a pace that was going to start initial testing in about 6 or 8 months. And I began to look at the situation, and the assistant division chief walked in my office one day and he said, "Ken," he said, "I know you well enough to know that if you get started on that certification startup process, you're going to stay with it until it's ready to run. Do you realize how long that's going to take you?" And I said, "Yeah, it's going to take 3, maybe 4 years in all probability." I said, "I've been there before." And he said, "Are you sure you want to stay that long?" He said, "You better go over and take a look at your retirement situation." I did. I decided it was time to walk out. I went to Bob Bauer, who was director of our aeronautics at that time, and I asked Bob, I said, "Bob," I said, "I think I've decided to retire if you'll let me name my successor." And he looked at me and he said, "I don't know whether I want to do that or not." I said, "Well, you think about that." I said, "I really don't want to stay for this project, but I'd like to name my successor." And he said, "Who's that?" I said, "I won't tell you until you promise me you will let me do it." And so he thought about it, called me back the next day and said, "Ken, come on over and see me." I went over and saw him, and he said, "I think I'm really willing to listen to you very attentively." I said, if you're going to listen to me very attentively, I'll tell you who I want to recommend." And I gave him the man's name. I said, he told me, I would have never thought of him. He was the man who was selected. He did a fine job, and I was thrilled to be able to do that. That was where I kind of was ready to walk out then.
What was his name?
Oh, now you asked me the question that I can't give you right at the moment because I've right at the moment forgotten it. Sorry about that. You know, as you get a little older and you don't remember people quite as well, you forget names.
Let me back up a little bit. I'm interested in your thoughts about computers and their application and the early days of wind tunnel testing versus today with the computers. Explain the difference a little bit and what it means to wind tunnel testing.
Okay, back in the early days, we measured forces with mechanical gauges, ordinary scales, for example, in the wind tunnel, in the full-scale wind tunnel. Then we began to use strain gauges, and so we had electrical outputs. We measured pressures with manometer boards and fluids in tubes, and we had to read those manually. We usually recorded them on film and then read them afterwards. But many times we simply sat there and read manometer tubes. We read the electrical outputs from strain gauges on meters and recorded that data manually. The computer technology allowed us to do something brand new. By the way, Langley's first computer, I was a witness to the first computation. It was located on the second floor of what we then called the 19-foot pressure tunnel building and occupied a room probably 30, 40 feet by 50 or 60 feet and consisted of just rows and rows and rows of racks of telephone relays, ordinary garden variety telephone relays. The first computation was a simple multiplication of 2 digits by 2 digits, and it took all of a couple of minutes to happen. as we listened to the clatter of telephone relays across the room. Of course, technology moved along rapidly. And we began to get computer technology. We began to get electrical systems that we could put the output voltages onto tape. And so some of our first data reduction was done by simply recording the voltages from pressure measurements, from strain gauge measurements onto tapes, and then using mathematical relationships to reduce that to data. One of the things we did in that low turbulence tunnel upgrade was to provide a facility with the very first real-time data computation so that the engineers would know what the answers were almost to the letter, you might say, right away, and could make the necessary changes in the test plan to get the data that they needed. Then final data would be reduced by a contractor with more detail.
I think I've asked you this before, but will the computer, they talk about making aircraft designs by computer, are we going to do away with the wind tunnels?
Oh, no. Wind tunnels will never be done away with. Everybody understands that knows the subject, even the theoreticians who like to claim they can do everything on computers. And by the way, theory is great. I wouldn't knock it one bit. But the problem comes from these things called boundary layers and viscous effects. We can handle the compressibility effects very well, but the viscous effects get to be a problem.
Viscous, what's that?
That's the boundary layer again.
Okay.
That's the real world in which we live, you might say. So as an absolute minimum in almost any case, you have to have a base point experiment that gives you what that boundary layer is really doing on the vehicle or on the surface. From that point, you can use very excellent mathematical techniques to make predictions of other configurations or modifications to that configuration. But there'll nearly always have to be some kind of a wind tunnel test some way. But it does reduce the number of wind tunnels we need, and it reduces the types of wind tunnels that we need.
Talk a little bit about that Coke bottle evolution, Whitcomb's Coke bottle, and how that actually makes it possible to get through the speed of sound.
Well, to go back to the very earliest tests, what we were working with was a simple wing body, just a body of revolution, you might say, that looked kind of like an elongated wiener, I guess you'd say, with a nice trailing edge on it that was kind of sharpened, and a simple wing. And we were running tests at the transonic speeds and observing the shock waves and making pressure measurements and force measurements. And what happens is, when those shock waves develop, they interact with one another and the drag goes up just markedly. Now, in order to reduce drag, you have to reduce the intensity of the shock wave. And, well, what does the shock wave do? It blocks flow. So if you can relieve the flow field by changing the contours, then the shock wave is reduced in intensity and hence the drag is reduced. So some of the very first clues, you might say, that we obtained as Whitcomb was working was to see a drag polar, as we called it, that was rising very rapidly in the high transonic speed range. We'd see 1 or 2 points slightly lower. And that was the clue to, hey, we can change the shape of this body, we can change the shape of the wing, we can reduce the shock waves and reduce the drag. And that's the background to all of the transonic drag reduction work that went on.
So this is the point of the greatest shock wave would be the interference of the shock developed by the fuselage with the shock developed by the wing?
That's right. Well, actually, it's the shock on the wing primarily, because that's where the supersonic velocities first develop in normal situation. And you simply shape the body to allow that shock wave to be reduced in strength. So the Coke bottle came about as a result of that. And everybody called it the Coke bottle, too. And it looked, in the early days, a little bit like it, I might say.
And what aircraft was that first used on?
That was the F-102. That was the first airplane that was used on. And by the way, the 102 did fly through transonic speeds as a result of it.
With the same power, or did they add a little power to do that?
I think that was with the original power plant, but don't hold me too tight to that one.
But close.
Very close, yes. Power plants were in the process of changing all the time, of course.
You had talked about a conference you attended when you were thinking about a small satellite launched from an air vehicle as opposed to a satellite launched from the ground, as I recall. Tell us a little bit about that experience.
Well, in my horizontal takeoff reusable launch vehicle system studies that I did in the 8-foot tunnel and some in the little hypersonic tunnel as well, one of the things that seemed to be coming out of that was that there was a need, or an apparent need, I should say, for a small vehicle that could transport just a few people and maybe some supplies up to some vehicle in space. But everybody was thinking in terms of big vehicles at the time. The Apollo picture was coming on. Gemini was well in progress at the time. And I had done work on the supersonic transport, which I hadn't previously mentioned, but that was part of our work there in the 8-foot tunnel. And I had viewed that as kind of an interesting thing because it had such large fuselage volume potential. Changing it over to make it carry an internal payload instead of people in the form of upper stages looked like a reasonable possibility to do something that the Air Force might be interested in. Because if you use an airplane launch, then you can use the aircraft capability to fly that vehicle into any orbital launch that you want. So you can now have a covert launch. That means you can put a vehicle in space anywhere you want to, and if somebody happens to be trying to follow what you want to do, it's kind of tough. They know where it takes off from, but if it's a vertical rocket, they know exactly what plane it's going to be in and where it's going to end up. Here they wouldn't. So what I did was take the supersonic transport technology, add some rocket engines to the back end of it, replace some of its volume with some hydrogen oxygen fuel tanks for those rocket engines, use that to boost the air-breathing capabilities of a supersonic transport up into the lower end of the hypersonic region, and then open a bay, drop out or push out an upper stage that would then go on to orbit. And that was presented, by the way, in a paper at a military conference in Dallas, Texas. In fact, I think I probably have I got a photograph of that thing right here, taken from what was at that time a classified paper, has been adequately declassified. But this was a beautiful drawing by our illustrators in color at the time. And unfortunately, nobody was interested in small vehicles. They only wanted big vehicles. So it didn't go anywhere.
Let me ask you a little bit about this new airfoil research in the Whitcomb. I don't quite understand how you can get lift out of this is a little arcane perhaps, but how you can get lift out of an airfoil with a relatively flat top surface and a curved bottom surface.
All right, well, lift, of course, is generated largely by the difference in pressure between the upper and lower surface. And depending on what Mach numbers you want to operate at, you can shape both the upper and lower surface to do the job in any fashion you want to. Now, by proper shaping, you can develop the proper pressure difference between the upper and the lower surface in almost any fashion you want. If you do it in such a fashion that you do not get large shock waves at early Mach numbers, you still get the lift that you need. Now, you're going to get the high lift by using devices, flaps and things like that on the trailing edge and perhaps leading edge. But for cruise lift, it's easy to generate that lift in the same way that you do with ordinary Clark-Y airfoils, you might say. In fact, one of the airfoils that was first proposed was basically a Clark-Y airfoil in which the upper surface was depressed somewhat to flatten it, to reduce the velocity gradients on it, and allowing it to bulge out a little bit more on the bottom, and it still developed a very nice lift curve.
Well, what happened to Bernoulli?
Oh, Bernoulli's still present. He still works just exactly right. We didn't violate any laws of Bernoulli in the process of doing that. We just changed the distribution. See, in an ordinary airfoil, most of that lift comes near the leading edge. One of the things we did was to distribute that across the upper surface in a more uniform fashion.
So you're still getting a higher speed flow across the top of that?
But not as high.
Yeah.
The acceleration rate is much lower.
Okay, let me ask you, looking back on your career in NACA, NASA, what do you think was the most significant contribution that you might have made to the progress of aviation and even spaceflight?
Wow.
Should have-
Yeah, are you asking for a single one? I don't know whether I can name a
Not
single one or not.
necessarily. What are the kind of the highlights?
I could kind of point to several highlights. I guess the fundamental work in air inlets and boundary layer was a very important one. Headquarters acknowledged that with some special acknowledgments, and everybody in the industry used it for multi-engined aircraft. That was, I think, a very important one. I guess the work that I did in conjunction with reusable launch vehicles during the years when we were simply studying systems became foundational to a lot of the things that ended up as Space Shuttle ultimately. The little jet plume work was kind of an offshoot, but that probably was a pinprick somewhere along the way. I guess I would kind of culminate it. Oh, the drag rise stuff was very important that we did. And that was a great deal of interest and lots of fun too. And finally culminating with the aviation, the Air Force research program.
Oh, okay, you said the drag rise, in what way? What do you mean by?
Transonic drag rise work. Yeah.
Yeah. And that, of course, gets into the Coke bottle
Sure.
situation. Okay. Well, anything else you would like to, one thing I want to ask you about. At one point, you had said you had a theory, and I can't remember what it was about, but your neighbor took a look at it. Tell us about that.
Oh, that was an interesting thing. Well, I had a neighbor who came from Germany, Dr. Adolf Busemann, who came to this country as a prisoner of war through Canada. And he lived just a couple of doors from me, and I had lots of good relationships with him. But I worked at that particular point in time for Dr. Sam Katzoff, who was a fine theoretician in the full-scale tunnel branch. And I was doing some theoretical studies and had completed one little study which I thought would show some important information. So I took it in to Sam one day, and I said, Sam, look this over. I said, you usually find what I do wrong, but if what I've done here is correct, this may be of significance. Well, he spent a couple of days and looked it over and came back and he said, I think you're right on target. He said, but just to make sure, let's go down and see Dr. Busemann and let him look it over, because he said, I don't trust myself on something this deep. So he made an appointment and we went down to see Dr. Busemann down in the old NACA headquarters building and a couple of blocks away. And we walked in and I handed him the paper, a document, and asked him if he'd look at it. And he glanced at it, looked at the summary on the front, and then he flipped over to the equations, looked at the equations, then looked at the end point of the equations, and he said absolutely nothing, smiled, walked over to an old file cabinet that he had brought from Germany, dug down into the bottom of it, and pulled out a very old brown folder that was almost ready to come apart. Out of it he pulled some, looked like almost newspaper material, and he said, here, let me show you. Back when I did this, Dr. Prandtl told me where I made my mistake. Now let me tell you where you made your mistake. I felt very complimented that somebody as distinguished as Dr. Busemann had done what I had done, or vice versa.
And who was Dr. Prandtl?
Dr. Prandtl was probably one of the most outstanding aerodynamicists in Germany and in Europe in that day and time in the 20s. In fact, Dr. Prandtl founded the Göttingen Institute in Germany. And it was under Dr. Prandtl that Busemann had all of his early years.
Well, I wanted to ask you, Busemann was, when you were working for NASA, he was your neighbor, is that?
Oh, yes, uh-huh.
And I think you said something about his wife's cooking?
Oh, my gracious, she was a marvelous cook. She made some of that German coffee cake that was just out of this world. And I finally asked her, because I like to cook a little bit myself, I finally got the courage to ask her if she could translate her recipe so that I could make some of her coffee cake. And she said, oh, she'd be glad to try. Well, some weeks later, she gave me a piece of paper with a recipe on it. She said, I'm not sure how well I've been able to translate this. And she's one of these types of good cooks that it's a little pinch of this, a little pinch of that, a handful of that, and that's how the recipe develops. Well, I tried to follow the directions absolutely explicitly. My coffee cake didn't come out the same as hers, obviously. By the way, there's another interesting little tidbit I might share with you. there was a man by the name of Jean Rochet. He was a little French engineer that came to this country. I'm not sure whether he was born here, I've forgotten, but he worked as a civilian at the Wright Memorial Aeronautical Laboratory. And in the early 1920s, as NACA was formed, he was named to be the connection between that laboratory and the Langley Memorial Aeronautical Laboratory. Well, he was a very fine engineer, and he designed in 1925 an airplane which turned out to be the first for-fun airplane ever designed or built in the world. Now, it was called the C-1, as most people know it today. He built it in the basement of his house out on Back River Road, and one day Henry Reed and Elton Miller and I think John Stack and several of them came over to see his airplane in his basement. And the question that was asked was, how in the world are you going to get it out of here? The wings were laying over against the wall, the fuselage was there, the engine was sitting in a crate, and he was getting close to the finish line, and he just smiled. Now, I've heard him tell this story a number of times, so I tell it from personal experience. But he said, well, we'll just wait and see. And a few months later, he invited them to come over and see his airplane. They came over, and here it was in his barn garage, all assembled, engine on, almost ready for first flight, which, by the way, I think they took it off from the road in front of their house there, Rockwell Road, which is now in Gosnow Park. But anyway, they stood there amazed and couldn't figure out how he got it out. Well, his plan was prepared, you might say. And what he did was, when he got ready to take it out, he called his friend who was a contractor. He came with his digging machine. They went to the back of the house, dug a nice big hole out of the foundation of the back of the house, removed a few cinder block and some of the foundation materials, cut a nice door in, put a storm cellar door type on with a nice concrete ramp leading up to the lawn. And he just rolled the airplane out. And that's how he got it out of there. That's fascinating. Now, by the way, that airplane was ultimately changed in nomenclature to be the C-2. It was repainted when the Aeronautical Corporation of America was established in Cincinnati. And it was built as a single-place airplane in 1929, and in 1930, a two-place airplane known as the C-3 was also produced. And that's the first real for-fun airplane.
And that company it was sold as an Aranca, is that correct?
It was sold as an Aranca, yes. And there are lots of them still around.
Anybody else have any questions? I think we got a good, one thing I might like to have you do, go back and talk about the Lindbergh experience and hold that book up. So we could can we do that? Okay. To go back to 1927 when you're driving down the road or whatever, and relate that experience, and then we can hold that book up and give it a shot, if you will.
Well, my dad had taken me by train to Dayton, Ohio, and we were staying at the Dayton Hotel in downtown when we heard an extra on the street that the Lone Eagle has landed. And Dad went and got a copy of that extra and brought it back to the room, and we went on to the funeral, family funeral, and came home. And that Christmas, my dad gave me a copy of one of the first print books of the book We, which became kind of my, you might say, encouragement into aeronautics in those very early years. Now, very interestingly, just a year ago, my wife and I traveled up through Minnesota. And for the very first time, I was privileged to go to the original Lindbergh home and see all of the artifacts in that home and talk to some of the folk there. So that kind of was icing on the cake for the Lindbergh story.
Ken, would you hold that picture up one more time?
Oh, the picture? Sure.